Hello, everyone. My name is Ranjit Narjala, and I'm a part of the Cloud Security Engineering Organization at Google. As a brief introduction, I started out my career a couple decades ago, and over the years, I've had the privilege to be involved with building products covering security, identity and authentication, networking, and platform technologies. I'm really excited to be here today, and thank you all very much for attending. Now, I'd also like to thank Sam and Renee for a great overview of what data governance means in the context of cloud. They really covered a broad range of topics, all the way from access control, data classification, protection of data while being stored as well as when it's in use, multi-party computation, and finally, incident and response management. So what does the rest of the session today look like? We'll start off with a slightly deeper look into our confidential compute portfolio and the risks that it actually helps protect you from. And then we'll dive a little bit more into confidential space, which you heard Renee talk about a little bit, and the use cases that this enables. And finally, we'll get into answering some of the questions that you all have submitted. So maybe first, let's just spend a couple minutes understanding why confidential compute is needed. Maybe we'll take an example, right? How many here would agree that owning a house or a villa in most of our cities is getting expensive, right? I'm not sure too many people are going to disagree with that. So what would you do in a situation like this, right? We perhaps opt for buying an apartment. The price point is lower. Common expenses are shared across all apartment owners. And in financial terms, we have a lower capex and a lower opex. Now, this is exactly what virtualization did to server hardware. Virtualization technologies and the hypervisor essentially helped create an apartment model for our server applications, which now no longer need dedicated server hardware. Now, what happens when apartment prices start to go through the roof? Well, maybe at that point we start to rent or lease, let's say, a serviced apartment. And this is what the public cloud enables in tandem with virtualization. You now lease server capacity, or in the apartment analogy, we pay for the space we use, but upkeep, maintenance, things like lights, cleanings, all of the common needs are taken care of by the apartment owner. Now, what would be our concern if we have to stay longer term? Some examples could be, is my privacy taken care of? Will my belongings be secure? Will my valuables be safe? Now, the apartment and the owner perhaps may have access to my apartment itself. How do I ensure confidentiality and privacy of my family, my assets, the security of my belongings? Now, in the public cloud model with shared infrastructure, one of the biggest concerns we've seen customers have is exactly this: the confidentiality, integrity, and privacy of the data and the applications that they want to run. How do I ensure confidentiality from other users of this shared infrastructure, as well as the infrastructure provider themselves? Now, the most obvious method to protect data is to encrypt it. Google has always provided automatic encryption of data at rest. This is something that is just done by default. Now, we also enable encryption of data in transit. But what about data in use? What happens to the memory at runtime? And this is where confidential compute comes in with hardware backed memory encryption that really completes the end to end data protection story. It helps provide mitigations from hypervisor vulnerabilities, rogue admins, user space attacks, and various memory attacks as well. So how does this work? Right? If you look at a typical cloud compute setup, we have at the very lowest layer your physical hardware, right? CPU, memory, perhaps disks as well. Next, On top of that, there is a host memory controller that manages the memory usage. And on top of that, you have the BIOS, the operating systems, the hypervisor layer. Now, the virtual machines run on top of this stack, and they have their own operating system and their own applications that consist of code and data pages, all in the guest virtual memory. Now, if you look at a typical setup like this, logical isolation of the virtual machines is provided out of the box. However, at the hypervisor layer, there is still direct access to physical memory. Now, with confidential computing, in addition to this logical isolation, we also add strong cryptographic isolation and integrity capabilities that are all provided by the CPU. Now, here you can see, similar to what Sam also shared, that a secure processor creates ephemeral keys for each virtual machine that are used to encrypt data before it gets stored in physical memory. And these keys are generated at every virtual machine boot and are non-extractable from hardware. This is really key. Even Google or the cloud service provider does not have access to these keys. Now, there's a little bit more to all of this, but fundamentally, this enables our customers to run their sensitive workloads in a protected environment in the cloud. Now, it's also important to note three things about our implementation of confidential compute. Number one, ease of use. As Sam just showed us, it takes literally a single button to enable a confidential VM within GCP. There's no need to rewrite or recompile your code. Anything that runs on a regular VM should run on a confidential VM. Secondly, performance. This is a big deal. Our customers typically see close to zero performance impact. Now, obviously, this would also depend on the actual workload that you're trying to run. And thirdly, scalability. We support up to 224 virtual CPUs and almost up to a terabyte of memory, 896 gig to be precise. Now, in addition, our confidential compute portfolio also attests to the integrity of the entire hardware and software stack. And this attestation is an important aspect of how customers can actually gain confidence that their workloads are running in the right environment. Now, today we have confidential VMs on GCE, starting with third generation AMD EPYC CPUs. With confidential GKE nodes, you can achieve encryption in use for data that is processed inside of your GKE cluster. Now, this is built on the same technology foundation as confidential VMs and keeps data encrypted with, in this case, node-specific dedicated keys that are again generated and managed by the processor. For big data processing with confidential Dataproc, you can create a Dataproc cluster that uses confidential VMs to provide inline memory encryption. Now, there's a lot more in the pipeline as well. But I'd like to dive into one specific aspect. The biggest driver of cloud has been the explosion of data and analytics. Right? Cloud has made ML and AI mainstream. There are so many of these data-driven applications that span multiple domains: healthcare, financial services, retail, and so on. Now, almost all of these AI and ML applications require one or more organizations to actually collaborate and share data. Now, unfortunately, many organizations today find themselves having to choose between innovation and data privacy because there is almost always personal or PII data as part of the information that needs to be shared. Now, obviously, organizations want and need both. And that's why we've introduced confidential space. Renee touched upon this a little bit, but this is a powerful way to enable secure multi-party collaboration with trust guarantees that are built on top of confidential computing. This is the next solution in our confidential computing portfolio. And organizations can perform tasks such as joint data analysis, ML model training, with the trust guarantees that the data they own can stay protected from their partners, including hardened protection against cloud service provider access. And this enables scenarios where collaborators can essentially gain mutual value from aggregating confidential data together, while importantly, still retaining full control over it. Now, before we get into an example or two to talk through how this can be done, I just wanted to take a minute and maybe introduce a few terms that we'll come across. First, we have the workload author. This entity person creates a workload that is to be run in the confidential environment. Now, the workload is really a containerized image that includes an application that has access to protected resources. The workload author, importantly, does not have access to the data or the results that come from that processing. Next up, the collaborating parties are the ones who own specific data that is private, but which they agree to share with the trusted workload. And finally, we have the operator who actually runs the workload in a confidential computing environment. Now, the objective of confidential space is really to allow for these trusted workloads to access confidential information from multiple collaborating parties. Now, with this background, let's look at an example. Now, Renee talked about a financial services example. I'd like to look at another use case that is in the spotlight right now. Now, in this example, we have healthcare organizations that want to, let's say, improve their disease diagnostics models. We also have an AI company on the right over here that perhaps specializes in developing such models. Now, one issue is that this company does not have the PHI or the personal health information data that's needed to actually train their model. But on the other hand, the healthcare organizations may not have all the resources or expertise needed to build a model like this. Now, there's clear value in collaborating, but only when it is done without exposing this private information. And this is where confidential space can play a big part. With confidential space, the healthcare organizations can share their sensitive data with this workload, knowing that only this workload running in a hardware-backed protected environment will have access to the data. And when all of this comes together, patients win because disease detection improves and no PHI is put at risk. Now, there's a lot that actually goes into creating a solution like this, and we probably don't have enough time to get into all the details here. But at a high level, there are three main aspects that are built on top of the confidential computing foundation. Number one, a hardened custom VM image running the workload within a hardware-backed confidential environment. Number two, we have an attestation service that verifies this confidential environment and then provides an appropriate claim. And finally, we have the federated identity piece that verifies these claims before protected resources, let's say decryption keys, are released to the workload. Now, confidential space helps generate a remotely verifiable attestation that includes information about the actual hardware-based trusted execution environment, the operating environment that's running, the unique identification of the workload, and the container configuration. And this attestation can then be used to confirm what code is actually being executed and the fact that it is being executed in a confidential environment. And then these attestations could be used further in conjunction with identity and access management policies to only grant requests coming from specific container images that are running with that particular configuration that I've already approved, and only if the workload is executing in a confidential environment. Now, we're seeing a number of use cases for financial services and insurance companies in fraud detection. We've talked through some of those earlier. We also talked through possible healthcare use cases, and this has the potential to significantly improve patient care. We've also seen use cases where retail companies can leverage confidential space to build data clean rooms, as an example. So, in summary, confidential space provides an ability to collaborate without requiring blind trust. Everything is measured and verified before you share your data. And you really, as the data owner, control how your data is used and which workloads are authorized to access it. And finally, you don't need to trust the operator or the admin either. And I think overall, we are super excited about the value that this is going to unlock for our customers and our end users. So, to sum up this particular part of the section, confidential compute really is an industry wide effort in secure computing. And we at Google, together with our partners, are innovating to further our security and our privacy guarantees. Now, confidential computing is not a silver bullet, but it provides one more layer in the overall defense in depth security story, especially for organizations that have highly sensitive data. It completes that end to end data encryption story with hardware based encryption and remote attestation. And as we've seen, it's easy to use, performant, and scalable. And finally, we have solutions like confidential space that build on top of confidential computing and enables a variety of new use cases. We've talked about secure data sharing, privacy preserving analytics, joint ML training, and more. With that, let me move next to addressing some of the questions that have been submitted. And thank you all for posting your questions. While we may not have the time to answer all of them, I've taken a stab at collating a couple of these questions and addressing some of the larger themes that I've seen. So let's look at the first question. When your customers implement Google Cloud, what's the big aha moment that they have? Well, I would say that there are usually two such moments that we've heard. The first one is around simplicity. There's a lot of work that is done to try and ensure that the most common use cases are taken care of right out of the box. A great example is what Sam showed us earlier. A very simple, easy way to enable confidential computing. Literally one checkbox or one button. And that's what we really strive to achieve. At least for the most common scenarios, we want to make it super simple to use. And of course, we also support more advanced scenarios and the ability to do more advanced configurations as well. In addition to simplicity, I would also add scalability. Often things that are simple are really hard to scale, and things that need to be scaled can get quite complex. But I think when we move to the cloud, the kind of scalability that we get along with simplicity is something that our customers have appreciated a lot. All right, the next question. How do we enable encryption within Google Cloud? To better answer this, let's look directly at Cloud Console. And I've got a few screenshots here to help me talk through some of this. Now, as again Sam showed earlier, guest memory encryption or confidential computing is enabled by a single click right as you configure the VM. This automatically picks the right underlying hardware configuration and enables protection of data in use. On the storage side, disks are automatically encrypted. However, customers can configure their own encryption scheme. And you can see that there are a few options available here as well. And finally, all VM to VM connections within the VPC or the virtual private cloud networks inside of Google's production network are encrypted, supporting protection of your data in transit. And these three options really provide customers the ability to protect their data at rest, in transit, and in use. All right, we'll go to the next question. How are Google Cloud VMs hardened to protect against advanced threats? Now, Sam had also mentioned something called shielded VMs a little earlier. Now, these are virtual machines that are hardened by a set of security controls that help defend against rootkits and boot and kernel level malware. They leverage advanced platform security capabilities such as secure and measured boot, a VTPM or a virtual trusted platform module, and integrity monitoring. And all of this is really enabled by default on VMs and on Kubernetes containers. And this is the baseline on top of which you can then also enable confidential compute capabilities. Now, I've taken another screenshot from Cloud Console to show the shielded VM options as we create a new VM instance. You can see that highlighted in that security box at the bottom of your screen. Now, what does each one of these checkboxes provide? Secure boot helps to ensure that the system runs only authentic software by verifying the digital signature of all boot components, and then also potentially stopping the boot process if that signature verification fails. Now, this helps protect your VM instances against boot level and kernel level malware and rootkits. The VTPM, or the Virtual Trusted Platform module, enables something else called measured boot, and it does this by performing measurements that are needed to create a known good boot baseline. And these sets of measurements are then compared with subsequent VM boots to determine if anything has changed. And finally, integrity monitoring relies on the measurements that were created by measured boot and lets you monitor and verify the overall boot integrity of your shielded VM instances. You can even configure and set alerts on integrity failures via cloud monitoring. Now, what's key here is that VTPMs and integrity monitoring are on by default, providing baseline protection for all your compute engine VMs. All right, so let's look at the next question. Sometimes smaller businesses means smaller teams and lots of multitasking. How might you propose protecting your information and customer data when most company team members currently have access due to limited resourcing? Now, this is one that perhaps a lot of us will likely resonate with. There is, however, no one size fit all solution, and the exact mechanisms are likely going to be specific to how a particular business is set up. But there are some best practices that I think we can generally keep in mind. Right? The first step, and this is again something we highlighted earlier on in the talk, is setting up those right data policies. Who needs to have access to what, when, and why should data be collected? What happens to this data? What is its lifetime? What are the roles that individuals in the company have with relationship to this data? Now, sometimes we may skip doing this upfront, and then trying to retrofit this over existing processes is usually a lot harder. As part of this, we usually need to identify what data, either internal data or from customers, is required. And ideally, we should be collecting and storing only the bare minimum. Sam also talked a little bit about access controls, and this has two related aspects: access transparency and access approval. Access transparency logs all access to data, and access approval lets you, as the customer, approve or dismiss requests for access by Google employees that may be supporting your service. Policies like this give customers additional control over their data. Now, another best practice would be to actually limit access to data where possible. Now, in a scenario like has been talked about here, this is actually especially important. Does everyone really need to have access to all of that data? Another good best practice is to use tools and software that comply with specific security standards and requirements. And this gives us the ability to correctly implement all of these controls. Now, there's probably a lot more that we can think through, but maybe I'll just add one more, right? Which is managing the life cycle of the data is also a very important practice. Things like deleting data that is no longer needed, putting processes in place for DLP, thinking through where data is replicated. These are all key aspects as well. All right, moving on to the next question. How do I use confidential computing within a Kubernetes cluster? Now, to take a look at this, let's actually go back to the Cloud Console. Now, in general, a user can enable confidential computing whenever a new virtual machine or a GKE cluster or a GKE node pool or even a Dataproc cluster is created. We took a look earlier at creating a confidential VM just by simply enabling it when we configured the VM. Let's take a look at the example, at the GKE example here. Now, confidential GKE nodes is built on top of confidential VM. When you enable confidential GKE nodes on a cluster or on a node pool, data in workloads that are running on these confidential nodes is encrypted in use. So let's create a new cluster with confidential computing enabled. This would mean that nodes in the cluster in any node pool will use confidential GKE nodes. Step one here is to configure a standard cluster. Next, we go to the security tab. And as you can see, there's yet again another simple checkbox to enable confidential GKE nodes. This would automatically change the machine types to those that would support confidential compute. Once you finish this process, you'll see the cluster being created. After creating a cluster with confidential GKE nodes, as we've talked about, any node pools created in this cluster will only use confidential nodes. And similar to creating a confidential VM, this is a fairly simple process as well. All right, we'll probably take one last question. Is enabling these controls the responsibility of technical teams or information security personnel? Now, it's likely going to be a bit of both in practice. There's going to be maybe different technical teams within an organization based on what the organization deals with. Different teams will be involved in evaluating how data is stored, where it needs to be stored, how it's classified, and what data needs to be protected. These teams will need to interface with InfoSec to make sure that these controls are actually in place. Now, in smaller companies or maybe companies that are really growing fast, these new controls will likely need to first be established. On the other hand, larger companies will have likely more established roles and processes, and enabling these controls will become the shared responsibility of multiple teams. And with that, I think we are pretty much at time. We've covered quite a bit of ground today, and I hope that at least some of it was useful. Now, all of this is also available on our website with more information on use cases, demos, documentation. So if you'd like to dive deeper into any of these areas, there is a ton of good information available. I'd like to thank you all for your time today, and I hope you have a great rest of the day.